Okay, so now we want to look at the concept of escape speed, right? So the idea of escape speed is how fast does an object need to be going to essentially, quote unquote, break the gravitational bond that it has with its parent body, in our case the Earth, all right? So let's look at a rocket, and it's initially on the surface of the Earth, and I want to give it an initial burst of kinetic energy. And I want to know how fast it needs to be going to break the bond of gravity that it has with the Earth. So this is essentially the same thing as asking, okay, what is the rocket going to do as it's rising? Well, we know that as the rocket's rising, it's going to be losing some of that kinetic energy as it gains potential energy, all right? So to completely break the bond of gravity, what it's going to need to do is be able to move off to infinity. It needs to be able to move to infinity, all right? But as it's moving off, it's going to be slowing down, right? It's going to start off really fast, and then it's going to slow down as it's moving away. And so essentially, to break the bond of gravity, what that means is it has to move to infinity, but as it's doing so, it will lose kinetic energy. And so once it reaches infinitely far away, it will have zero potential energy, but all of its kinetic energy will also be exhausted. If it does not move to infinity, then it was never able to break the gravitational bond. So what this is essentially saying is that initially the gravitational potential energy is negative. So I have to give it enough kinetic energy so that the total energy of the system is zero. Because if I apply the energy conservation principle, my initial energy must equal my final energy. Once I'm at infinity, I have zero kinetic energy left, and I have zero potential energy. So my energy of my system is zero at the end of my system. Therefore, it needs to be zero initially. So what that means is, I can say that since there must be zero energy in my system, that means I need to give it a kick of kinetic energy of 1/2 mv squared, and that must add up with the potential energy minus g m1 m2 over r. And in our case, this is the mass of the Earth, and this is going to be the radius of the Earth, okay? So if I want to calculate what velocity I need to give my rocket initially, now rockets need to achieve this speed, okay, but they aren't given just an initial burst of kinetic energy. They get continual thrust from their rockets and so on and so forth. But, right, let's see what happens here. I can move my gravitational potential energy term over to the left-hand side of the equation, and that gets rid of my minus sign, and so I'm going to have g m1 m2 over r, the radius of the Earth, right? And again, this is going to equal 1/2 mv squared. But 1/2 mv squared is the kinetic energy of my rocket. So if I consider m1 is the mass of the Earth and m2 is the mass of the rocket, then the m in the kinetic energy term represents the mass of the rocket. So this is also m2, all right? So this is also m2, and so my m2s cancel out. And you'll see that the escape speed actually does not depend on the mass of the object you are trying to lift, all right, or propel. And so all I need to do now is multiply both sides by 2, and I'm going to flip the equation around. So if I multiply both sides by 2, I get v squared is equal to g me over re times 2, right? And my last step is to simply take the square root. Now, when you take the square root, you do need to be careful about how many roots you're going to have, but in our case, we know that we're going to be interested only in the positive root. Or, in other words, we're interested in the magnitude of my velocity. Okay, so we're kind of ignoring the direction. And that's why sometimes this is called escape speed as opposed to velocity. But anyway, there you have it, okay? So if you want to calculate the escape speed of any planet or star, all you need to know are the object's mass and its radius. And you can then calculate what the escape speed for that object is. So if you want to know the escape speed of Mars, for example, just get on Wikipedia or an astronomy textbook or whatever and look up the mass of Mars and the radius of Mars, and you'll be able to calculate Mars' escape speed, which will be smaller than the Earth's because it's less massive and it has a smaller radius. Actually, the smaller radius would contribute to a larger escape speed, and that's something that's rather interesting. When you play around with your masses and radii, you'll see that. You can also calculate the escape speed for the moon, say, for example. But this is the formula how you do it. A lot of people make the invalid assumption that all you do is set your kinetic energy equal to your potential energy, the magnitude of your potential energy. And the argument is actually a little more subtle than that. Again, the whole argument revolves around the idea that at infinity, your energies are zero, and that's why you can set them equal to each other here. Okay, it's not just that your kinetic energy must equal your potential energy, it's that both of your energies go to zero. As you're rising away from your object, you're losing kinetic energy, but you're gaining potential energy. And so, since your potential energy was initially negative, as you're gaining potential energy, your potential energy is going to approach zero. Your kinetic energy was initially positive, so as you're rising, you're going to be losing that and also approaching zero. All right, so there is a subtle point in your argument. It's not just that your kinetic energies and potential energies have to equal each other. Okay, so do be aware of that. All right, we'll see you next time.